Well, hello everyone. Welcome to, in a way, Trump. My name is Brett Thompson. I'm in the Laser Product Group, based here out of Connecticut. So I'm at home right now. My friend and colleague James is at the Smart Factory, or I'm sorry, the main factory doing the actual hard work for us, running the 5030 fiber. So I'm going to run through some advantages of our um, compressed air cutting processes. We have normal compressed air cutting processes. We also have the ability to use some of our special nozzle technologies that I want to introduce to everybody. So we're going to go ahead and we're going to start with a little bit of a presentation. When the presentation is done, we're going to hop over to the laser and see everything live. Now, if everybody looks, you can see kind of in that back corner there, that back corner, it's my cat, Charlie. He's promised me not to get up to Dickens. If he does, please somebody warn me. So he doesn't surprise me and sneak up on me and kind of ruin the whole thing. So what we want to do now is go through, like I say, a quick little presentation on the different sort of ways that you can go about using compressed air cutting. But why might we use compressed air? What's the interest that we have in doing so? Now, when we use compressed air as a process, it's still a fusion process, kind of like nitrogen. There are a couple different ways and a couple different limitations that kind of push us in a certain direction. So pretty much all of us have like a rotary screw air compressor or some big industrial compressor that can provide us with a decent amount of pressure, but a good amount of airflow. And so that's going to have kind of a limited range. So it already exists, that's a good thing, but because it can't really generate a lot of pressure, we have a limit with really how thick the material can go, right around the 120 thousandths range. So you do have, as another alternative, what's called a dry air assist system, and you see these becoming more and more popular. Now, with a dry air assist system, you're going to have a bit of an initial investment, but the nice thing about that is you can generate pressures and volumes that are very similar to nitrogen, and so that obviously has a benefit. So definitely the downside is that you're going to have to make an initial investment, but you're going to achieve kind of the same thickness limitations, the same sort of capacities, the same sort of cut speeds you would with a high pressure nitrogen process. So we have a couple of different nozzles that are available that we can use. Now, looking at the different nozzles here, we have what we call a high-speed Eco nozzle. And with a high-speed Eco nozzle, we have this little retractable sleeve, okay? So this is gonna allow us to basically create a nice surface contact with the material, force all the gases through. And with that, it's gonna give us the ability to really cut with much lower gas pressure. So we're looking at about 87 PSI as our maximum pressure here. When you compare that in the left column, and we look at something like this is our standard, what we call EAA nozzle. This guy requires higher pressures because it's only a single orifice. Compare that with the high speed with the sleeve, or the high speed Eco with the sleeve, or the regular high speed nozzle. These are both of the images you see on the right of the screen. You see there's kind of a dual orifice here where we kind of stabilize those gas flows. Since we have a greater offset to the surface of the material with this regular nozzle, what we have is, of course, a greater requirement for pressure. So we can't use, kind of low pressure processes because this guy's so far away from the surface of the material. We really got to crank out a lot of assist gas in order for us to be able to eject that melt. You can see with high speed nozzle technology, what we have is a contact with the surface. So this little guy here is going to sit on the metal, right on the kerf basically, and it's going to force all of the assist gas through. And so this allows us to get away with using really low pressures and also about doubling the speed because we're making efficient use of that gas. We don't have to kind of back down the speeds a little bit to accommodate for the proper ejection of that material. So now when you look at the standard process against like a high speed or high speed Eco process, there's a couple things that we have as a benefit again. So one is going to be a big reduction in gas consumption. The other is going to be a big reduction or a big increase in speed, so a pretty substantial reduction in processing times. So this is a little video that will show a little side-by-side comparison between those two processes. So one thing that you want to notice with a high-speed Eco compared to a standard process, it's not just the cutting speed. You're going to see good straight-line cutting speed in the comparison. But what you're also going to notice is a difference in the piercing time. Since, again, we're having really good, efficient use of the gas, we can cut a lot more quickly, but we can also pierce more quickly. And so you'll notice that when it's hopping from position to position, the pierce time in 1/4 inch, like we see here, is about 0 seconds. So that's considerably faster than you would have with just a normal nozzle technology. Now, with the Highspeed Eco, the sleeve is really an important aspect, right? And so we get the question, how long is this little sleeve going to last? And the answer is generally about a shift. So you get about 8 hours out of one of these. If you want to have similar cut speeds and you want to have similar edge quality with still a pretty good reduction in gas, you can use the Highspeed nozzle because it's not containing any consumable bits like you have here, this little 3-piece design in the Eco technology. The thing with the Eco, though, and what's really unique about it, is that it rides on a little cushion of whatever you're cutting with, so compressed air today or nitrogen in other scenarios. And so that allows it to be very flexible. So its normal offset from the surface of the material is actually about 10 millimeters or so. So it is touching the surface of the material, but you can see if the material is not flat, the nozzle can adapt. So this video is going to show how it's able to adapt going over checker plate, which is, I'd say, a pretty severe scenario. So what you're seeing, the little lines that are already on the part, that is just a pre-etch for the pattern so you can see where the laser is going to go. Now it's at normal cut speed. It's going to slow down so you're going to be able to see more accurately and with higher detail what's really going on with that little sleeve. So you can see when it goes over the checker plate, that it's just, it's like a little bit of suspension. So it's adapting to the surface. Now, this will probably consume the sleeve a little bit more quickly. So if we're cutting with this sort of process on diamond plate or something that has a rough texture like this, you might go through the sleeve a little bit more quickly. But that's really the upshot to a nozzle like the Highspeed Eco, or again, indeed the Highspeed nozzle, is neither in really either of these cases do you have to worry about having the nozzle really being so close to the material that becomes problematic. So basically where it's potentially hitting like a little bit of slag bulging, a little chunk of 1-inch stainless steel. And you might have to, with other nozzles, be very gentle on that pierce, because if it's sitting right off of the surface, it's going to hit that. So since we have a normal offset, like I say here, about 10 millimeter, like 3/8 of an inch, and with the Highspeed, also kind of a normal offset, you don't have to be concerned about how efficient you can really process. You can be aggressive with the pierces. If you get oil on it or anything, it doesn't matter. It can go back into the nozzle changers. No real issues with it. So as a practical example, this is not exactly what James is going to run for us today. Some of the little bits I've been holding up are what James is going to run. But we just kind of ran a scenario here because I want to look at consumption and then cost in relation to consumption. So the piece that you see here is 1/4-inch stainless steel, and we ran it on a 10 kilowatt machine, a 5030. So what we did is we ran it in a number of different scenarios. So let's consider your standard nitrogen cutting process. So again, this nozzle, the EAA, and then high pressure air, which would be with this same sort of nozzle, just with that generation system where it's creating the 400 or so PSI that we might need to cut with. And then we have the Highspeed Eco technology. And we're using Highspeed Eco for 2 different purposes. So we have nitrogen. So again, if I pop up this big old chunk of 1 inch here, that is Highspeed Eco with nitrogen. This is with compressed air. In the actual materials that we're cutting, this is what it's going to look like. So you can see the edge quality looks a little bit different, but you're going to be using that same Highspeed Eco technology to cut either of these parts. And they're going to be at roughly the same cut speeds. So what we have here is, of course, quicker cutting time and less gas consumption. And that's a really important thing, because when we're using, let's say, 50% less gas to cut this part because of the Highspeed Eco with even nitrogen in this scenario, you are, of course, reducing the amount of consumed gas per hour. But when you're doubling the cut speed, which indeed is what happens in 1/4-inch material, you're also using less assist gas per part. And that's just because it's taking less time to cut the piece. Regardless of how quick you're cutting, the consumption is still 1,024 cubic feet per hour. So you can see that your consumption values go down quite a bit. The reason you see a little bit higher with the air process here is because we're using on the stainless steel actually a high-speed nozzle in this scenario, as opposed to the Eco, but either one can actually be used for this purpose. So when we consider an actual production environment, so again, the laser, we have the cost of the laser. And so I'm using the investment value of the laser, my payoff period for the machine, the amount of floor space it takes, and you're coming out to, let's say on 2 shifts, about $70 an hour. That's what I'm considering for my base cost for the machine. And then we also have to consider labor rates, labor utilization, material costs and use, this gas, electrical, those sort of things. So it takes the amount of time we showed here in the previous slide to cut a single part, but we want to apply that to an entire nest. So we cut 76 parts. It's 2 sheets worth. And basically what that gives us is a total job cost, including the biggest component, which is the material itself, but also a substantial portion of the cost, which is the amount of assist gas that's going through this little nozzle. So what you'll see here is that your total job cost, that's what we got here, right?
Brett,
yes?
Sorry, from the IT side, might I interrupt you to ask that all of the attendees mute yourselves? We seem to be picking up a little bit of background noise, and just so everyone is able to hear properly, can everyone just check their systems that you mute yourselves?
Okay, so I was muted for a moment, but I think I'm unmuted, so that's good. I think maybe Slay doesn't want me to talk anymore. Maybe she does. Nevertheless, when we consider the cost of the process, we consider how much time it takes to cut the part, and then the amount of gas that's being used. The time and the gas consumption are going to be the variables that affect these costs that you see here. So again, we're cutting the 1/4-inch stainless steel with compressed air, and we're cutting it with nitrogen, just with different processes. Standard nozzles, NAAA, or Highspeed or Highspeed Eco. And so you can see that the production costs for just the standard nitrogen process, they're the most, because we have to consider not only the cost of the machine and all those other things, but this consumes the most of gas. It actually consumes a little bit less than the compressed air, the standard compressed air, if you will, with a generator, but you have to pay for the nitrogen. So we're buying it in bulk, that's the assumption. With a compressed air generator, you're still reducing the cost. So you have a benefit there. You can see that you've knocked about $200 off of the cost of the product, even though if we go back to the previous slide, it's using more assist gas, if we will, but you have a much lower operating cost because all you have to do is, kind of your calculation on the investment of the system. They're relatively inexpensive to operate. So that's a cheaper process than just the normal nitrogen cut when you're, again, using this nozzle. When you get into the biggest savings, though, you start using the Highspeed or the Highspeed Eco nozzles. So again, some of the reason that the high speed part here was the second to the cheapest piece at you can see here we're a little bit less than we were with the standard piece. A lot of that's going to come down to the cutting process time, because again, you have the material that you have to consider. That's your big cost. You also have the labor uses, all those sort of things, but of course nitrogen. So when you look at the cost of the compressed air process, because we got rid of the nitrogen, this guy again, it has the lowest process cost. So it's going to be the cheapest part. And then when you look on the graph on the left, the right of that one, you can see how much the actual assist gas cost is associated with the part. So really substantial cost savings with these nozzles. So when I'm considering whether I can cut with compressed air, kind of have to consider what my situation is, right? If I don't have a Trumpf laser, what you need is one of the dry air assist systems. And of course, you're going to have to buy that system. There's an upfront cost associated with it. If you have a Trumpf laser, the consideration is, do I have the availability of Highspeed or Highspeed Eco? Do I have these nozzles available for me? If you don't, you would have to go to a dry air assist system. So since it's on a lot of the machines we have now, pretty much the whole range with the 3 and 5 series lasers, some things with the 1, if you have an older machine or if you have a CO2, you don't have that availability. If you do, then you don't have to purchase anything. You can see here there's no cost. You have everything that you need because you already have your compressed air supply to the machine. So this is what the availability looks like on the different machines being produced. If you have questions and you say, I've got a machine, maybe it's a couple years old, it's a fiber 3030, let's say, with a 6 kilowatt, is it available? Just contact me at the number that you see here. And we'll also send that information out afterwards. And if there's a question, we can certainly look it up and see if you already have it or if it's something that's retrofittable. So what we want to do now is we want to go into live cutting processes with my friend and colleague James at the factory. So he's in front of our 5030 fiber. He's going to step through some of the parts that we saw here. So what we're going to go ahead and do now is we are going to make James the presenter. And you have the floor, my friend.
Hey guys, how's it going? Today we're going to show you a bunch of different materials on our 5030 12 kilowatt. Going to run through some of the compressed air cutting that we do here and some of the topics that Brett touched on. So first, we're going to start in the more traditional sense with the standard nozzles, show you guys some thin materials, and then we're going to jump into some thicker stuff, go to the max range for air cutting with steel and with stainless steel. So first, let's jump into the machine and cut some stainless steels. So for you guys today, I have some 120 thousandths of an inch 304 stainless. We'll just get this set up here. We have this cool tool that's on the machine that we can actually use to quickly change tech tables on our various different programs. So if you program something incorrectly or you just want to change it to a different tech table, it's pretty flexible and easy to do. So first we're going to cut with our standard nitrogen tech table to give you guys a taste of that, show you what it looks like. I'm going to drive my laser here over my sheet and set my position and let it go. So this is our 5030, like I said. This is going to be cutting at 826 inches a minute, I believe. It's a 120 thousandths of an inch thick material again. Right now we're doing a nozzle change. You can see it there. It's a 21 spot changer. It's going to go do a control line calibration now. So that's basically our height sensing system. That's what we use to actually sense the sheet and know where it is so that we have the proper offset for our nozzle distance and our focus is always in the right spot. Going to do a little bit of etching right there, nice Trump logo, and then it's going to jump around the sheet.
If I can interrupt a little bit, you are a little bit off the camera from what I'm seeing, unless I'm in the wrong aspect ratio,
Yep.
perhaps.
Nope, I see it.
Okay.
No big deal. We'll stop that and move it over.
Yeah. So what would be interesting while James is changing that position, what's cool about cutting with compressed air with the high-speed Eco nozzles, and indeed really with a dry air assist system, is it really is extremely close to what you would have as a parameter set for nitrogen. So if you said, okay, well, you know, I've got one of the Trump machines and it's got high speed, it's got Highspeed Eco, but I don't have tables that got 1/4 inch steel with compressed air. Well, what you can do is you can simply just create a copy of the nitrogen table, just change the assist gas, and you might slow it down a little bit, you might not, you know, just judge it based on what the results are, but they're actually extremely adaptable.
All right, guys, we're all set up and ready to go again. Sorry about that. So now you can actually see what I'm talking about. There's the laser etch right there. And again, this is nitrogen cutting. 826 inches a minute on 1/8 inch stainless steel.
And this is what laser, James? This is a 12
This
kilowatt?
is our, yes, this is our 12 kilowatt 5030, the
Okay.
big boy.
Big guy, yeah.
Go in and grab that part and show it to you guys so you can get a look at it.
Yeah, absolutely. And the great thing about that machine, and this will be, you know, we don't want to have all the fun stuff dealt with today. We want to have a reason for y'all to come back. This machine has what we call active speed control on it. So in the near future, we're going to do another webinar where we highlight that feature, which it very much is autonomous. It's the closest you can get to being totally automated with a machine. It's a technology that actively looks at the kerf and it says, okay, the material quality, she's not so good. We've got a little bit of rust on the surface. The material is inconsistent. It's just some random A36 somebody dropped off on my my loading dock here, I need to cut, the laser will automatically adapt. Conversely, if it says, hey, you know what, this material is actually pretty good, it will speed up to 20% over what the base, 15% over what the base feed rate was. So you'll either go slower to make sure that the process is consistent, or it will actually go faster if the material can support it. So that'll be something we'll be doing in the future.
All right, guys, we're all set up and ready here. So this is going to be, again, 1/8" stainless steel with compressed air now. This is going to be actually a little bit faster. This is going to be 1,106 inches per minute.
That's actually pretty substantial.
Yeah, you'll see it do a nice etch there. And you can really see the machine's drives take control of that speed and really use it to its full advantage. And there it is, done. Go in there and grab this apart. And it is
so in this scenario, we were, what, roughly 300 inches a minute faster than nitrogen?
Yes.
Yeah, that's substantial.
So yeah, they've been doing a really, really great job there. You can see the side edge there. This is the underside of the part here. So if I can get it in close, you can see it's burr-free. It's got that oxidized edge that Brett was talking about before. So it is a little brown. It's not silver like the nitrogen cut.
And to clarify too, at 120 thousandths, this is the maximum we can do without special nozzles, right? Low pressure nozzles.
Correct.
Yep. So this was the normal limitation, folks. So we were able to go up to 120 thousandths before, because that's really about the maximum pressure that you can get out of your machine. That's the maximum thickness that can be achieved. So with the Highspeed and the Highspeed Eco, rather than seeing really high pressures like 400 psi, 380 psi, kind of in that area for the thicker stuff, your pressure is actually closer to 75, 80 psi. So it's really, really low. So you have the ability to drastically expand the range till, in fact, actually on stainless steel, you can go up to 1 inch. So the low pressure technology is really what allows us to, to increase the range without having to buy a special system.
So on to our next material. We have some 3/8 stainless in here. I'm gonna do a nitrogen cut on this. This is gonna be the Highspeed Eco, so that touchdown nozzle that Brett showed you guys before. This is going to be running at, I believe, 5 bar of nitrogen pressure, 3 bar of nitrogen pressure. It's gonna be going 267 inches per minute using 12,000 watts. Again, doing our nozzle change here. And you'll actually notice that on some of these nozzles, it'll do a little bit different of a control line calibration. You'll actually see it kind of swirl around. It's actually calibrating that active speed control that Brett was talking about before. So a little tidbit in there. Cool thing about this nozzle, we use it for a lot of different scenarios. So it's gonna work from 160 thousandths of an inch to 1 inch stainless. It's gonna work from 160 thousandths of an inch to 1/2 inch steel on this 12 kilowatt laser. Same thing goes for the 10 kilowatt.
So what we're doing by creating a circle, James, what was that? We're centering the beam, right? So we're checking.
Yeah, it's looking at the beam. Yep. Mm-hmm. Which is another cool feature about this machine. It will actually yell at me for going too slow. I had the potentiometer turned down there, and it'll actually stop the machine, so it won't let you make any dumb moves. So we'll just re-enter into this. But it actively looks at the beam center. It actively looks at the cut to ensure that it's a good quality cut. There you go. You can see that it pierces really, really quickly. Again, 267 inches per minute on that 3/8 stainless. And again, that's with nitrogen. Pull this out and show it to you guys. And I'll lift it up. There we are. And actually, even though I had my potentiometer set at 70%, still cut. It's actually only in that centerpiece that it was doing that. On the outside, it was full speed, 267 inches per minute. You can see a really nice edge there. No burr. That's the underside right here. Really nice, straight, really perpendicular cut. Really nice. All right. So we're gonna now do the same material, so 3/8 stainless, but we're gonna switch to air. And again, I'm using the same program for most of these, just quickly changing the tech table using this quick change tool. This is on all the platform machines, 10 series, 30 30 series, 50 series. Really, really handy. So this is going to be going a little bit slower here, 204 inches a minute. And we're going to use a different nozzle now. We're going to go and switch to the high-speed nozzle. So that's the dual orifice nozzle that Brett was showing you guys before. Place my part. And again, another nozzle change. And my potentiometer is at 100% this time.
That's certainly a good thing. And
Yeah.
just so everybody knows, I see some questions popping in. So at the end of the operation here, we'll take a couple minutes and go through the questions that you all have. And then, like I say, you folks have our contact information. So if you think of something later, you get woken up like I do thinking about lasers. I suppose that happens with normal people. You can just shoot a message and, we can address that later. Or, you can come in and see it for yourself. So what's the pressure on that, James?
So this is also using 3-bar. So again, the really awesome part about these nozzles is it allows you to use, the stuff that you're already hooked up to the machine with. So if you have the high-speed nozzle or high-speed eco nozzle available, then it makes it really easy to just switch over to do these things. Pull this bad boy out, and there it is.
Certainly. So 3-bar is about 43.5 psi, and out of your normal screw style air compressor, you can get, I think, generally a max around 125 psi. So we're well under the capacity of our air compressor.
All right, on to the final stainless steel, our 1-inch. So again, this is going to be the max capacity for air cutting. You can go thicker on this machine. It's got a lot of power. To use nitrogen, you can go a little thicker, but we're a little limited on air cutting just because of the lower gas pressures. Right. And again, it's going to use this high-speed nozzle. So this is 1-inch 304 stainless steel. This is going to be cutting at 28 inches a minute, and it again uses 3-bar of air.
Wow, it pierced in that time?
It's almost through. That's its first stage, and now it's through.
Can you explain what the stages are? Because that's, I think, pretty interesting.
Yeah, so what we're actually doing here is we are piercing with oxygen. It's a multi-stage pierce, pretty standard to our thicker stainless steel cutting. It allows for a really stable pierce that's also really quick and clean, doesn't leave a lot of spatter on the surface. That's really a big concern. In the past, there were stainless steel pierces where it kind of left a little mountain on the top of the sheet or a big spatter. This oxygen style pierce really goes away from that, which is really nice. You can do smaller features with this style pierce, and it's also really fast, which is cool. A lot faster than a nitrogen pierce would be.
So this is also using bright line fiber, right? So we're activating the outer core.
Actually, with this tech table, we're using a 210 micron focal diameter. So we're actually using the core, not the sheath of the fiber optic cable. If you were to cut this with nitrogen, you have a few different options. You can go with a bright line tech table. So that would use a larger focal diameter, 600 or 840, somewhere in that range. You also have your high-speed eco, which on this machine, being a 12 kilowatt, is extremely fast. It's around 48 inches a minute with the 12,000 watts, which is really fast, and it pierces even faster than the pierce that you guys saw there because of that special nozzle technology.
Yeah,
So let me pull this out.
I find that interesting because I see you can even see the part drop in the sheet.
Oh yeah. So nice and easy to come out. Really nice. And it's very hot. I don't know if you guys can see my hands smoking here.
Hopefully it's not your hands. Hopefully it's your gloves.
Yeah. Get it in there. Really nice looking part. Nice and straight. I'm going to put that down because it's very hot. And give you guys, just show you guys this. This is the bright line. So there you go. Just to give you guys a taste of that. All right. So let me exchange my pallets now. Let's switch gears in material, and let's move on to our steel. I had to just clear my light barrier there. Now the pallet should exchange. Beautiful. All
What's
right.
that
So
I see on the plate there? Did you cut like a family crest or something for your house? Is that your last name?
no, it's actually the Trump logo.
Oh, thought you were in the mailbox business or something.
Yeah. So you guys can see that I have two different materials on here. I have some thin steel and some thicker steel. I'm going to start with the, again, standard nozzle technology. It's going to be an 080 steel, and we'll start with nitrogen. So I'll drive over there.
Maybe bumper down the sheet a little bit, James, so we can see.
Oh yeah, no
You'll probably
problem.
be okay, but let's waste some material. There we go.
There we go. That looks good. Perfect. All right. So again, another nozzle change here. Going back to the standard nozzle, so that single orifice nozzle. You're going to use nitrogen for this. I believe that it is cutting at around 2,000 inches per minute. Looks like somebody modified this tech table a little bit.
Which is probably incidental, right? This is all about machine dynamics when you get into the thin material.
Right.
And the
So
cool
we're
thing
gonna,
about the nozzle change, so y'all will notice that we're not worried about alignment or anything. So you also notice we're screwing the nozzle in. When you screw the nozzle in as opposed to pushing it in, you don't have to worry about the alignment of the beam to the center of the nozzle. So it allows us to go quickly and reliably from nozzle to nozzle.
yep. So again, a laser etch there, and it is just flying. So this is going to be using 13 bar of nitrogen. And man, that thing goes. All right. Pull this part out here for you guys. Show you guys this. Hopefully you can see it. It's kind of thin. Again, it's 80,000 steel cut with nitrogen. This is the backside right here. So if, let me get it close for you guys. Check that out. Smudge there. Really nice. Trump logo. Very cool. All right. So same material. Let me just flip my sheet around so you guys can see this a little better. All right. Perfect. And now to cut with air. And again, this is going to be that same standard nozzle style, just with air. Right. Again, super easy and quick to change this. So we're going a little slower here, 1,840 inches a minute for our air cutting. And let it go. I actually think that this uses the same nozzle, so I don't think it's going to change. Oh, nope, I lied. It is changing. All right, our final control on calibration, and it's off to the races. So this is using 5 bar of air pressure right now, so a little bit higher than our stainless steel counterparts. Awesome. Open this up and show you guys. You'll notice that it has a little bit different edge than the stainless steel. I don't know if you guys have ever cut with air before, but you'll see that it has a black edge on it instead of a kind of burnt orange edge. This is the underside right here. So get it nice and close. See if you guys can see that. Really nice, clean, burr-free. All right. On to our final part. So let's move now to our little bit thicker steel. So this is our 1/4" steel. And we're going to start with nitrogen. Just move my sheet up a little bit for you guys. Then move my laser for you guys. Perfect. All right. So again, this is 1/4" mild steel. We're going to be using nitrogen. We're going to do another nozzle change. It's a good thing that this machine has such high dynamics with all these nozzle changes. It does them so quickly.
That is certainly fortunate. Is this using active speed control also?
It is.
Okay.
I believe it is, yes. Yes, it is activated. So it is actively monitoring its cut, and it is speeding up and slowing down as it sees fit, which is really handy. You know, if you guys have a varying steel that you use, anything like that, it becomes really, really helpful. It also can increase productivity, which is nice.
Yeah, I believe the average increase across the board. So if you look at your nitrogen range, even your oxygen range, so it's pretty much all the materials, it averages out to about 7% increase over feed rate, which is substantial.
Wow.
But like I say,
Doing
that's
a little edge.
another webinar.
And there it is. Oh, and we lost it. That's okay. I luckily have one on my table over here I can show you guys. So that was 486 inches per minute in 1/4" steel. So here's the part. This is what it looked like, a little lead-in mark right there. Get a close-up of that beauty. You can see this is the top side. You can see our little trump etch right there. And we look at the back side, really nice, burr-free part. It's ready to go on to get painted or wherever it's gonna go. No need to clean that up. All right, so now let's go and use air. So this is, again, going to be a little bit different than the stainless steel, as we're going to employ this special nozzle, our Highspeed Eco nozzle. This is going to be going 450 inches per minute, so it is a little bit slower. That's pretty typical of air cutting with steels, but air is really inexpensive, which is awesome. So this uses 6 bar of air, and again, 430 inches per minute. You will see it do a nitrogen etch, so you'll see it purge the gas after it does its etch. So it's purging right there. It's going to put air into its sysgas chamber, and then it's off to cut. And like Brett was talking about before, you'll see this thing pierce, and it pierces right up in the air, which we call fast piercing. It gives you a pierce time that is almost 0, if not 0. Let's pull this out of here. Oops. Got it a little wedged in there. No big deal. But take a look at that. So again, this is the top side here. We'll see the bottom side there. And you can see, oh, there we go, really nice. Again, burr-free, you do have that black edge on there, nice shiny edge. That does not flake off like a normal oxide. That's hard, so you can paint over that. There we go, oh, that's nice. Really nice part. A little hotter than the nitrogen one though. Must be that oxygen in there. All right.
Perfect.
Well,
Well,
guys,
so maybe we have a couple questions here. Maybe we'll hop through some of them. One good one for you, James. When we're using the Highspeed Eco nozzle, what would be the minimum distance we need between parts? So what's the web that we have to work with?
so when we're programming with our Highspeed Eco nozzle, we like to go with a 5/16 spacing, so 0.31 or 8 millimeters. That's just to accommodate for the nozzle's larger spot size kind of on the material, how big the nozzle footprint is itself. That's just to ensure that you're not hitting it into parts or anything like that. And actually, if you look, that I believe that's actually our standard spacing anyways. With the tapered nozzles or the single orifice nozzles, you can go a little bit closer, but typically 3-1 is where we're keeping it.
Okay, great. So, and that's a like we say, a reliability feature, because if we have overlap with the nozzle on another part, we'd lose the cut, right? Yep, so
Correct.
it's a process reliability feature.
Correct.
So we have a question from Douglas Miller regarding the cost calculation. So the total job cost is the total job cost. So that's machine, labor, electrical, materials, and assist gas. That's broken out separately from, in the total job cost does include the gas cost, but we broke out the gas cost as its own standalone figure. And yes, we're using nitrogen in one scenario, we're using compressed air in the other, but you're looking at the cost of the assist gas. So it doesn't really matter that they're different gases. It's just, what are you paying for the thing to eject the material out? And that's basically what drives the cost calculation. And I do have sheets that I can share with folks. So if you say, hey, I think this sounds interesting, we have cut speed charts that we share with people, and the cut speed charts include the cubic feet per hour of consumption. We have a chart that we can use to correspond that to actual gas usage. So if you have like a time estimate, James says, I can do this sheet in an hour, and it's 500 parts, you can actually do a calculation to see what the actual gas costs are, basically. So just let us know if that's something you would like to see. So as far as the filtration requirements for the machine, so what that is, it's the exact same thing that we would have in the pre-installation manual. So if you have a current Trump machine, you have the ability to cut with compressed air. Now, whether you can go up to the thicknesses that we're looking at today, that depends on whether you have Highspeed or Highspeed Eco. And so if you don't have it, and it's a CO2 machine, unfortunately, you're out of luck. If you don't have it and it's a fiber, well, you might be in luck if it's a 3 or a 5 series machine, but there's going to be a point where we can't actually do a retrofit. But if you're not sure whether it's possible or not, just let us know. We'll look it up and we'll let you know if it's something that can be done. And certainly we could come in and do the retrofit. It's fairly simple. Now, as far as, so let's see. Now, I think this is a good one from Shane Simpson. Do the edges on stainless using air need to be treated if painted? Well, it depends really on what the purpose is. And we do have customers using this for really, really thick processes. If we were looking at food service, medical, something like that, absolutely you couldn't use compressed air, because obviously we're cutting with atmosphere, you're going to contaminate the material. Now, for this, one example that I'm thinking of, these folks make structural components. So it's really not an issue that you would have, long-term pitting of the materials. The reason you won't put it in medical or food is because you would contaminate whatever it's in. So if you got, a bunch of tea sitting in your cut stainless steel component, you're going to give people, I don't know, tetanus or something. So it's best to avoid. But for structural components, it absolutely is something that is worthwhile. So another good question. So there's mention of stainless steel and carbon steels, but what about aluminum? That is a good question. Aluminum is actually applicable, and that will be kind of captured in something else we're going to do. And really, so when we're cutting aluminums, in a lot of cases, we'll cut with nitrogen, certainly, but also compressed air and with oxygen up to a certain point. So with oxygen, you create a plasma that allows us to go just ridiculously fast. That does have an upper threshold too. So it's a scenario where basically you have a stability issue when you get above 1/4 inch or so. But when you go up to 1/4 inch, your speeds are like 3 times what nitrogen are. In that same range, you have the ability to cut with compressed air, and the speed kind of falls somewhere in between the two. So nitrogen's the slowest, oxygen's the fastest, and you got compressed air somewhere in the middle. Now, the reason that some folks who might have, relatively new Trump fiber machines and they don't have the ability to do what James is doing today in steel, is because we're always working on processing parameters. So you can do an update to the control, you can get the steel parameters. What we'll probably see sometimes in the future is maybe not the Highspeed Eco, but with the high-speed nozzle, potentially we extend the range of compressed air cutting as well in aluminums. We mostly focus on where the most customer demand is. So people are saying, I want carbon steel and stainless steel, so we've been developing the processing parameters for those materials. But we'll certainly have, an ever-expanding way of cutting the different kind of metals and thicknesses. So, kind of keep your eyes open for that. As far as cutting thinner materials, so 3/8 stainless, the range was 160,000. What that's referring to is 160 thousandths of an inch for the high-speed Eco nozzle. So what we really find is that when you go below 160 thousandths, and it could be a little bit arbitrary, honestly, on a 4 kilowatt, we go a little bit thinner. So there we go to 120,000 because you'll actually get the speed benefit out of the nozzle. When you go below those values with these big machines like this 12 kilowatt, essentially what you find is that there's really not a whole lot of benefit to using a nozzle like this because it's too fast. So it might say, okay, I'm bringing my 2,000 inch a minute cutting speed up to 4,000 inches a minute. And even though this laser has just ridiculous dynamics, you're not going to be able to really see that translate into increased throughput because the machine's constantly trying to accelerate. So again, it could be something that is introduced in the future. And if you have one of the nozzles, you can certainly create your own tables. It's fairly easy. But as it is right now, that's kind of the practical limit we say. That doesn't mean that it actually is a limit. So with a 6 kilowatt laser, the maximum thickness, well, that is going to be depending a little bit on whether we're talking compressed air, but I assume that's what you're referring to. Obviously, that would make sense. It's a little bit less than nitrogen, so you can do 1 inch with nitrogen. Compressed air is 3/4 of an inch, so you do have a little bit lower capacity, and that's just a function of the lower laser power at that point. So we have on our big 12 kilowatt, I think our capacity for stainless nitrogen is 1.5 inches or slightly above. And with compressed air, it's 1 inch right now. Whether that's because that's the parameter set or whether we can't, with the pressures available, get past that point, I think it's the pressure issue. So you would probably see on the 6 kilowatt that the upper threshold will remain at 3/4 of an inch. So when should you use the Eco versus high speed? When it comes to the compressed air cutting, in some cases you don't have the choice in stainless steel, and it's a weird thing. So when you go over to Europe, the customers over there get delivered for quote unquote free with the machine. They're going to get high speed. They're not going to get Eco. They have to pay for it. We give Eco to our customers for free because we love our customers. And so we say we're going to deliver on the 3 and 5 series machines, both the high speed and the high speed Eco. And so the initial parameter development and why you see it on stainless is only for high speed is because it was global. So we're going to start incorporating high-speed Eco into more of these processes. High-speed Eco is always going to create a cheaper part. Sometimes it's faster, and actually sometimes high speed will be faster. Generally, high speed is always the ideal way to go, but if you have just maybe limited number of sleeves, or some people realistically, when they're running really high production volumes, unmanned operations 3 shifts a day, sometimes they prefer high speed because they don't have to actually deal with the sleeves, because usually what you do is you would have multiple whole bodies inside the nozzle changer. So you can change manually the sleeves by yourself, but the machine can't change the sleeves by itself. It can only change the whole nozzle. So you would have to buy the whole assembly multiple times that way. So it kind of depends on what your production environment looks like. Yeah, we can certainly share, some of the processes that we have, or I'm sorry, the presentations that we have with people. The black edge does not wipe off, so this isn't an oxide layer like you would get with an oxygen part. So if you rub your thumbnail on it, what I'm getting right now is mostly just my thumbnail rubbing off a little bit. Actually, let me make myself the presenter again.
I actually got you, Brett. So okay. I have a part right here. So we have this nice black edge right here, and I have a nice piece of stainless right here. And I'll I'll just scratch it, and you'll see it doesn't do anything to it. It's not an oxide edge like an oxygen cut. It doesn't fall off or flake off. It's kind of part of the side now. It's part of the edge now. So no worries on that. It's paintable. It doesn't come off.
Yeah, and that is, it's an important fact, because if we're cutting with oxygen, certainly you have to have that edge treated before you can paint it or before you can weld it. With compressed air, there is oxygen that is, obviously influencing the material, and that's where your contamination is going to come from in your stainless. Like we say, that's why you can't use this for food service or medical. But the oxide is really burned into the material, so it won't flake off, and that's why you can paint directly on it. And usually, it depends on what your welding process is, but you can usually weld it as well. If it were, a laser weld or something where you have a very, very low heat zone, you have to use nitrogen. You're going to have bubbling and popping. But for like a MIG weld where you can spread that, quote, contamination around, you won't have a lot of porosity or issues with, inconsistent or consistent roots within the, consistent contamination within the weld root. I'll be able to figure out how to talk by the end of this, I think. So I think really at this point, we'll probably shut this down. I see everybody's kind of hopping off here. So there are a number of questions left, folks. So if you didn't have your question answered, it's not because I'm trying to avoid your questions or, I'm trying to avoid you as an individual. Love to talk to you. So use my contact information. Get hold of me and we can discuss whatever questions you have. And like I say, if you're interested, we can do a live demo for you where we do something, just one-on-one with the same format that you saw today. Or even if you would like, you can visit us in Connecticut, in Chicago, or in our facility out in the LA area. So we certainly thank you all very much for your time. Hopefully this was informative. Hopefully it leads to further questions, kind of, get you scratching the head a little bit. And we'll see you for the next webinar. Thanks all.
Thanks, guys.